So I've got two disclaimers before I start. One, I always run late. I always run over. So blessings on the person who has this classroom next. And also, I do a lot of participation, question and answering type thing. Don't be shy. There will be a trivia. There'll be a trivia question session after, and we have door prizes to give out for the trivia. Thank you, Mr. Maples. 7 questions, 7 gift cards. So hopefully, and not, obviously it'd be good if we had different people responding to the actual questions. So anyway, for those who don't know me, my name is Tom Bledsoe. I started Bledsoe Imaging Group about 3 years ago. Been around the block a few times. This handsome young private, 1982, graduated from biomed class. Few things about me. Like I say, Bledsoe Imaging Group. I'm a consultant firm for digital radiography systems and also room removals. Tom and I have hooked up over the last couple years with some projects and stuff, and look forward to continuing that relationship very much. Taught virtually during COVID for the College of Biomedical Equipment Technology in San Antonio, Texas, CBET. And most proudly, one of the things I'm most proud of is this organization, this show, CAMI, the Association for Biomedical Instrumentation. And then one of my main hobbies is camping and horsing around. So my wife and I load the beasts up on the trailer and hit the trail and have a good time. So that's a little bit about me. Mobile and portable. So these two terms kind of sound similar or interchangeable, but there's slight differences. We in the field throw these terms around kind of loosely, portable and mobile. So I just thought I'd right off the get-go, I'm going to mix the terms, so don't get hung up on that at all. But mobile, the definition for mobile just means movable, right? So typically, not all the time, so typically those are like a portable x-ray machine that you see rolling down the hallways of a hospital. They're capable of higher kV values, 90 to 125, and the MA values of 40 to 300 typically. Portable means a compact transportable device. So if you think about the Army, like a MASH hospital or out in the field, they can't wheel around these huge portable X-ray machines. They do make them rough terrain mobile X-rays for the Army, but that's not what we're talking about here. We're talking about any kind of like something that you can even hold in your hand now, and I've got a few examples later on in the program. The technology that's happening in dental right now, I'm probably going to mention this a couple times. It's going crazy with now they have one that looks like the base of a DeWalt drill called the Nomad, and you just double click the trigger. They hold it up to your jaw. It's a battery operated X-ray tube, and they put a digital sensor in your mouth, and it's just like having the old bite wings. And you've got an image like in 3 to 5 seconds, and all it does is use a USB cable from the sensor to a laptop or a computer in the dental practice. So those are the main differences, mobile and portable. Again, I'm going to use them interchangeable. We do it all the time in the field. So there is a distinct difference if you drill it down. The portable ones are not capable of the higher KVs. They're used for, like I said, in Army or dental or something. If you just need a quick picture, trauma case or something like that, handheld with a digital, we're going to cover digital sensors and how we grab the image off of that and then send it to a computer or cellular signal up from the battlefield or something like that. They do have, the Army has them pre-packaged from the manufacturer in some kind of backpack, cushioned backpack type of scenario, right? So portable versus mobile, this is kind of what I was talking about, little picture. So the first thing that stands out, you know, the one we're used to seeing in healthcare centers and hospitals is the mobile, uh, mobile X-ray. Uh, can somebody tell me, just a wild guess, why do we need, we've got X-ray, why do we need it to be mobile? Courtney? Well, icebreaker.
Because it's easier bring that to the patient and the patient.
Bingo. We have some patients that can't come to our X-ray. Already? No, trivia questions separate from real question. So we can't always bring the patient to the imaging center, the ER, whatever. So a lot of times we have to take the technology to them. If you picture an ICU bed, an ER bed, you know, can you imagine trying to take this person, put them on a stretcher, bring them down to radiology and all this stuff, right? So we have to take the technology to them. So you know, we have both mobile and portable solutions for that. So see the little backpack deal that I talked about earlier. You got your handheld in his left hand. The unit that's a lot. This laser's not working real well. There we have the mobile X-ray on like a tripod stand in like a MASH unit or an urgent care thing in the battlefield, taking a picture of that soldier who was injured in combat or whatever. And then another thing that I like to dive into a little bit, just because of my love of horses, is the equine veterinarian. It's kind of the same kind of deal. You can see the guy, he's got his lead apron, he's got his little, he's got his mobile X-ray handheld and the digital panel on the other side of the horse's leg. You know, so these are just some fits for what we're talking about. The Nomad device in the center of the screen there is what I'm talking about. It looks like a base of to me, it's a DeWalt drill. They used to have battery problems with this, but recently they've changed them to like the rechargeable, just like a dock that you'd have in your garage for your drill motor, right? Courtney already answered this. We can't always, we need the patient can't always come to us. And these are some of the purposes this is a very short list. There's many, many more, but let's say the patient is injured, you know, would be bad to move that patient, right? ICUs, post-surgery, ERs, those kinds of things when it's not practical at all to transport. Veterinarian applications we just saw a picture of, and nursing homes and prisons, off-site medical facilities. You know, before I put this slideshow together, you know, some of these didn't even think about how do we get, you know, if you've got a aged loved one in a nursing home and they need an X-ray to try to get them out of that nursing home into an ambulance to the medical facility, get the exam, to get them back. I mean, you know, think about it. If you could take a portable X-ray machine, you know, on a large van, delivery van or something, and wheel it right in there, and you got your pictures there. And then this is kind of an off the thing, but I see it used a lot. Is person reports to the ER with an injury, the X-ray tech comes down there, takes the shot, the ER doctor's looking over their shoulder right at the screen. Now that's not a diagnostic image yet. That hasn't been sent to the archive. That's not an official record yet, but it gives them, is the arm broken or not? Is something out of place? Is there any foreign objects embedded in the kneecap or something? You know, those kinds of things. So it gives the physicians, surgeons, for instance, too. So it gives them on the spot quick reads on what's going on with that patient, right? So before I get into portables, I think it's good to go back a little bit and discuss what components are necessary to make digital radiation in a regular rad room. Obviously, we have to have a high power generator, because at the X-ray tube down here in the lower center, down in the lower center, we're going to take either 380 volts three phase or 480 volts three phase. We're going to turn that into 100,000 volts across the X-ray tube. And how do we do that? We do that with a high power generator. X-ray tube is the heart of the system. Without the X-ray tube, we have no X-ray. We're going to go into a brief discussion of how X-ray is actually generated and dispel some myths. I know people that don't normally work in this field probably have all kinds of ideas that you've heard from coworkers, family. You know, you walk into the room and there's X radiation floating all over, and you're going to glow in the dark, and you're going to be sterile, and you know, all this stuff, right? I've been doing this a long time, and I can tell you none of that is true. And we have you're going to see a few slides that's going to explain how and when the X-ray beam is on, and then more importantly when it's off, right? We have to have a way to control the X-ray beam. So mounted to the X-ray tube right over here, we have something called a beam limiting device, or a collimator. So what that does is that has lead blades inside of it, and we can control the size of the X-ray beam coming out of the X-ray tube. X-rays come out of a tube in a cone fashion. If you picture an upside down ice cream cone, that's how it's leaving the X-ray tube. So it's divergent as it goes out. So it not only spreads wider, but gets weaker the distance that you give it, right? So if we have a collimator with lead lined blades, lead is an excellent X-ray blocker, right? It absorbs all the X-ray. Then we can control the size of the X-ray. Picture the difference between a chest X-ray and like a wrist. So I can use the collimator to collimate down just on the wrist bones, and I'm not exposing a large area like 14 by 17 on the digital panels or the cassettes, right? We have to have a user interface to tell the system what kV we want, what mass we want, what time we want, you know, the different anatomies, you know, whether we're going to use automatic exposure termination, things like that. So we have, here we have an example of a operator console. And then another, if the X-ray tube is the heart of the system and we make our X-ray, we get our picture, we have to have a way to grab that picture and to send it to our main processing computer, and then later on to our archival or our PACS system. And that's done with, nowadays, done with you'll hear it called a bunch of stuff. You'll hear it called a panel. You'll hear it called this. I call it a digital flat panel, DFP. That's what I call it. You'll hear it from, I went to a site this year and they called it a board. They said, our board is broken. I'm like, I don't fix boards. You know, they meant the flat panel. They called it a board. Okay, I can kind of see that. And then to support our X-ray tube, you know, we have some kind of positioning device. You'll see a couple examples in the slideshow, but mainly in a regular typical radiology room where they just do rad shots, you'll have a tube either on a floor mounted situation or a ceiling mounted situation. And then we'll normally have a four-way float top table, so we can position the patient underneath where the X-rays are going to be coming out. And then for chest X-rays, skull work, shoulders, and that kind of thing, we'll have a wall stand that the patient will actually stand erect and either go PA or AP depending on the type of examination. They'll put their chest against the board. Typical chest X-ray, your annual physical, you know, you'll put your chest against the board, and they'll take a picture of your ribs and your lungs, and then you'll turn sideways. That's lateral, and that's taking a picture through your body laterally. So that's all done at the chest stand. So those are the main components. If you go into any rad room, then these are what you're going to see. So what do we need for mobile X-rays? The exact same thing, right? We're not going to have a table. You like that antique? that's that's going back a few years. Courtney used to use that back in Tennessee, didn't you? Yeah, past tense, past tense. So again, we have a way of generating high voltage X-ray generator. We've got a control console. Heaven knows on this one, it's probably big Frankenstein type knobs and stuff. We have our X-ray tube. See that little tiny X-ray tube up there and collimator? The collimator is basically just a lead cone, and in these days, they didn't have movable blades or anything. So it was just a cone to direct the X-ray. We have a way to support the X-ray tube on our column. And in these days, of course, image receptors, we just noted this film, right? That was our image receptor of the time. So then there's something known as, and these are in existence. These are a little more complicated to work on, but it's pretty straightforward. It's where we take an analog X-ray system like an AMX4, the most popular portable X-ray machine on the planet, and we make it digital by adding the components of a computer, digital panels, and then a user interface, so we can capture that old-timey analog signal. We can capture, make it digital. We just call that a retrofit. So the same components are used and needed on those, with the addition of we add a computer either under the covers or a laptop on top of there somewhere, and then we have a digital panel and a way to view that on a screen. I still see these around quite frequently. And now we have our full-blown digital mobile X-ray machine. The differences here is the computer is built into the machine. It comes with a digital flat panel. And the user interface is usually either a standalone computer or an all-in-one computer that's built into the system. So nothing changes much on the portable world, right? We just have to put wheels under it and make it battery operated, right? Yes. Yes, sir.
Some recycle places they won't take it, but I understand that it's basically cooking oil.
It's very high quality, very pure cooking oil. And back in the days when we had transformers, they called them PCB. I couldn't even tell you what the acronym stands for. It was cancer causing some kind of circuit boards or something that was in the oil that they did some testing on and found it carcinogenic. Right. So nowadays, there are companies like yours that deinstall X-rays, right? You don't normally have to worry about inside the X-ray tube because that's in a metal case and everything, and normally those are going to be sent back to be reloaded. They're going to take I just happen to have an insert right here. They're going to take the insert out of the casing, and they're going to put a new insert in, because the one thing that goes bad on these is just the filament. It's like a light bulb, like an incandescent light bulb. And right. I would contact the local recycler and say, I've got some high quality oil. It has no they're going to know what PCBs are. That's old days. That's old days. What do you do with the transformer? It's full of oil as well. Right. You don't know what they do with it. So you got to have that trail, that trail of ownership that, but yeah, mainly, it's funny that you say you normally make the hospital responsible, because the way the hospitals feel about it is we're going to make somebody else responsible for it. That's like pulling out a computer and you got a hard drive with patient information on it, right? It's like, we don't want to be responsible for that. Back in the day, we used to take those and take them to a drill press and just run a bit through the hard drives. There's programs now that do all that stuff for us, but yeah, I would just contact, in my career, I've never had to recycle a transformer with oil in it. So I would just maybe call, and you know, you're going to get the runaround. You're going to get like, no, we don't do that. All right. I'm going to stop right here for any questions because next thing is going to be a little intense when it comes to electronics and X-ray tube theory and stuff. So any questions out there so far? Courtney, I know you got something.
So far, you haven't got over my head.
We're about ready to.
Yeah, when we work together, Christmas, we don't want to be talking.
Yeah, we never let Courtney have real tools. Okay, so if there's this thing called radiation and it's bad for you and it's dangerous, why do we even bother? Why do we even bother putting staff at risk, patients at risk? Why do we fool with this stuff? Anybody? What's that? Amen. Without radiation, we can't get an inside look at the patient's body without splitting them wide open and doing exploratory surgery. So back in the day, if you had, you know, a leg problem or something, well, you know, cut you open, find the broken leg, fix the broken leg, sew you back up, months and months of recovery, whatever. Now we with the advent of X-ray and William Rankin, we have this technology. You're going to hear how dangerous it is probably from people that aren't in the field, and just the term radiation gets people's attention, right? I mean, it works. But if you're using it, I've been doing this for 40 years. I usually have a radiation badge on me that's monitoring the amount of radiation I'm getting. I can tell you for a complete fact, I've never had a reading on that badge. We're going to talk about time, distance, and shielding. We're going to talk about ways to protect yourself while you're working on it. If you're smart around it, there is no danger. I kind of parallel this with high voltage. When you're working around a high voltage, you're cognizant that it exists and you respect it, but you're not afraid of it. And that's the way I like to look at X-rays. Without X-rays, you know, heart cath, you couldn't Aunt Sally, you couldn't see her blocked arteries, and the doctor puts a balloon or a stent in there and opens it back up, so she's healthy once again. You know, broken legs, pneumonia in your lungs, your ribs. You know, we would have no way. The risks do not outweigh the benefits of radiology because we get an inside picture of what's going on. For the little amount of exposure that you're going to get, you could get the same thing by walking outside on a sunny day and walking through the parking lot, and 15-20 minutes out there, you're getting the same thing as like a normal chest X-ray. So radiation exists in our atmosphere and in our ground naturally. Everybody heard of radon? It's a real thing that's in the ground. It is radioactive and it can cause trouble over a long period of time. So it is in our environment. We're using it as our benefit. I usually go over, you know, we've already asked if there's any myths out there, but I don't know, does anybody have any fresh ones? I've probably heard them all, right? So Wilhelm Rankin, November 8th, 1895, we just celebrated this event last week. Rad Tech Week is normally held the first week in November for a reason. He was playing around and in his lab at the University of Würzburg in Germany with something called a Crookes tube. It was a glass tube with an anode and a cathode, hooked a vacuum to it, vacuumed all the air out of it because electrons flow better in a vacuum. And he was putting some voltages to it, doing some testing, noticed that the glass glowed and was wondering what this phenomenon is. So weeks go by, he's doing some more testing. One day he happens to have photoluminescent plates 6 feet away on his workbench. And he happened to look over and notice they were luminescing. They were lighting up every time he put the high energy to the X-ray, to the Crookes tube. So then some more experimenting. At one point he took black cardboard box, put it over the X-ray tube, energize the X-ray tube, and the plates still would luminesce. So what is this? What is this phenomenon, right? That's causing this light, this mysterious light, to light up these plates, even though it's covered with black cardboard box. Through this invention, some more testing with his colleagues and everything, they wanted him to name this discovery Rankine rays. Well, him being not a proud person or a very humble person, said he didn't want his name associated with it. But so the term X-rays came to us because X is an unknown, right? In an algebraic function, in math, X is your unknown. So that's why it's really basically and simple how we come up with the term X-ray. It's an unknown. Basically, I could tell you, nowadays, with some tweaks, modifications, we're still making X-ray the exact same way as we did way back yonder. So we just celebrated RadTech Week this last week. Professor Rankine was noticed as was the first Nobel Prize in Physics winner, 1901, and his statement when he got the award was, "I did not think I investigated." Very humble guy. Another one of my heroes in radiology is Madame Curie. You know a lot about her, maybe some things you didn't know. She had the first mobile X-ray service in World War I. She took ambulances and repurposed them with mobile X-ray. She was the first one to coin the term radioactivity. I didn't know if you knew that. She brought X-ray into the battlefield using a mobile unit called a Petite Curie. That was the name. She trained nurses how to take X-rays. You might want to remember Petite Curie. That could come up later. You might want to remember that. But here's why I respect her, and this is why I put this slide up there, is because of her statement here. Nothing in life is to be feared. It's only to be understood. Now is the time to understand more so that we may fear less. So that goes back to my statement about knowing X-ray exists, knowing where it's at, using safe practices, and respecting it and not fearing it. So during my slide presentation, you're going to see this little guy pop up. Guess what? That might be a trivia question. Just a little wink, wink, nudge, nudge for you. So somewhere on this page, there's going to be a trivia question. I kind of gave it away already. Courtney, are you paying attention? Now everybody knows. Well, that's the point. That's the point. So producing X-ray. What is X-ray? What is it? How can we define X-ray? Well, guess what? It's electromagnetic radiation, just like all this stuff over here, right? When you microwave your popcorn, you're using electromagnetic radiation. If you turn on your heater and you're feeling the heat from it, you're experiencing radiation. Going into the visible light, how do our bodies differentiate between brown and white and green? It's all a frequency of light, right? You'll notice the wavelength on the top of the slide, the frequency is getting faster and faster and faster. The faster you go with your frequency, the more penetrating power that you develop. So we can go from our natural light, our visible light. This is how we see colors. This is how the body interprets that. It's another form of electromagnetic radiation. Then we move into the ultraviolet light, where you have to start wearing some protection, right? If you walk out to the sun without sunscreen, you're experiencing radiation, and it can affect the DNA. It can affect your cells. And we're going to get into that in a little bit too. Then we get into our subject, X-rays, right? This is called ionizing radiation. It's also called, that's where it is on the spectrum. Right at the ultraviolet section, before that, we have non-ionizing radiation. Big word, what's it mean? Ionizing just means it has the capacity to change the DNA or cell structure. Now, I know that's kind of a shock statement, but again, using it safely. This is over doses over a long period of time. So don't want you to be concerned about that. But that's what ionizing radiation means. And then, you know, you get into the gamma rays. Don't know how many people work on nuke med systems, but we actually use radiation to our benefit now to kill cells that we want to kill, right? So, you know, longer doses, higher doses. You can see the frequency is really fast penetratable, but you know, that poor person with cancer cells and we want them gone, we use radiation to purposely kill those cells. And there's our Crookes tube, lit up and glowing. And again, here's like a pictorial of how we're going to produce X-rays. We need a high negative on the cathode. We need a high positive on the anode. We're going to give off this radiation, and we're going to use that in some type of receptor. We're going to put human anatomy in the middle of that beam, and certain beams are going to be passed right through. Certain beams are going to be blocked, and that's how we get the shades of gray on our image receptor. If you think of a chest X-ray, bones are white, lungs are dark. So radiation penetrates the lungs very easily. There's nothing really to stop it. A bone like a femur, a shoulder, skull, that's harder mass, that's harder material. It's harder for X-ray to pass through it, so it blocks some of it. That ends up being white on the film. I'm going to say film a couple times. I don't mean an actual X-ray film. Image. No, it's an image. We don't call it film anymore. So a little bit about, I'm going to try to roll through this quick because again, I always run over. But to me, I can't eliminate any of these slides and make my slide presentation smaller. I just, you know, I could, but it wouldn't. So anyway, we have a process here. How we get started is we have a process, big word, thermionic emission. What does that mean? That means we run current through a filament. The act of that energy going through the filament, it does something we call in the industry boil off electrons. It emits on an atomic level, it releases electrons, right? We run a current through a wire, a filament, and it starts boiling off electrons. So there's this little cloud developing around the filament. We have ways of focusing and using electronics to focus that cloud into a really tight formation. We don't want it like a mass. We want it like a tight formation. So if you just pause right there, so we have filament, current, we're boiling off electrons, there's a cloud waiting for there. What did I say in the early part? We need high positive and a high negative to draw those electrons across from the cathode to the anode. And once they're drawn away right there, right? A bigger, this stupid laser's not working. A bigger pictorial right there, and this is the moment that X-rays are produced. When we put that high positive and high negative, those electrons are drawn at a very, very fast rate, the speed of light. And the collision of those electrons into that anode target, that tungsten target, gives off energy. That energy is radiation. So the only time that I have radiation is when my hand is on the hand switch and I'm running those electrons into the anode at a very high rate of speed, and it's giving off that energy. Once you let up, radiation gone. It's not floating around the room for days, you know. And then we have ways to control that. But you got to understand, with the advent, when we went from film to CR and now to digital, we're full digital now in most cases. The sensitivity of the electronics in those are so tight that we don't need the amount of energy we used to have to darken film. So when we used to have an exposure of so much mass at so many seconds, now we're down to 50 milliseconds, 100 milliseconds. So we're only actually making radiation off the anode for that little bitty time frame. And we're still capturing all the data. In fact, we're capturing more data now on digital plates. There's just all the information is there. Not going to spend a lot of time on the voltage, how we generate that, just the essence of time. But we have a low voltage section of an X-ray generator and a high voltage section of an X-ray generator. Low voltage, we usually save that for controlling the electronics that's going to produce our high voltage. So if you think about your kilovoltage, your kV, if you think about the tube current, which is different from running the current through the filament, we're talking about while we're making an exposure, there's current running through the X-ray tube itself when that electrons are going to go hit the anode. That's called tube current. So that's called MA. When you hear the term MA, that's what that is. And then time. We have lower voltage electronics that are going to control our actual X-ray exposure. To get that high voltage, remember what I said, we're going to go from 380 volts, three phase, or 480 into the hundreds of thousands of volts, 120 kV, 110 kV. So we use a really nice step-up transformer. If you have a typical transformer physics is if you have less windings in the primary and more in the secondary, your voltage is stepped up. If you have the opposite, you know, it steps down. So we use both in the X-ray generator. We step up the voltage, of course, to get our hundreds of thousands of volts. But in our filament, we use a step-down transformer. Typically, see these in the range of about 24 volts AC, and that's what runs your filament wire, and that's what boils off the electrons. That's called filament. So there's a separate transformer just for that. So we run these high voltage cables out to our X-ray tube. I have an example here. So, you know, this is carrying 75,000 volts on each side up to 150,000 volts across the X-ray tube. So they're normally put in these specially designed ports, and there's only one way that these can fit in. We're going to cover that here after a while with that. Yes. All right. So so we have high voltage on the anode side and the cathode side. We're drawing this current through the vacuum tube. It's being passed around. We got it. Somehow it just switched screens on me and right in the middle of everything. So what we're passing around now is just the insert of an X-ray tube. So you're going to see the anode and the cathode. This is most radiation systems have a small and a large filament. Yeah, we're good. We're good. So that's basically how we generate our high voltage, how we make X-ray. Now you can kind of start seeing that X-ray is only there for a very short period of time, right? It's not flowing around the room in all kinds of directions. You're walking right into a fog of X-ray that's gonna, you know, affect you mentally or physically or anything like that. So I don't mean to make light of it, but if you understand the technology and the way it's produced, it makes sense to me as an engineer. And it's like when people come up with these myths, part of my job is just say, no, you've been watching too many YouTube videos or listening to people, you know, that don't know what they're talking about. Again, Madame Curie's definition of that was to understand it. So, like I said earlier, X-rays can only do a couple things. They can either penetrate or be blocked by structures in the human anatomy. That's how we get shades of gray onto our digital flat panel. We've gone through from trying to darken X-ray film to reusable CR plates with that has this luminescent material inside that's pulled out of a cassette, run through a digitizer, scrape the image off of that, reload that into the plate. All of this takes time. If you think about the moment, like say a typical chest X-ray, they take you in the room, they line you up, beep. From that point, you know, the doctor needs to see that. You know, that's valuable information. Like you said earlier, you know, we're looking for that information. The longer it takes to process that, the patient is sitting. They'll have them sit in a chair and wait for my image to process to make sure I don't have to do a repeat or something like that. With digital, we're talking 10 seconds. We're talking 12 seconds that from the moment the X-ray technologist hits the button to when they see a picture on the screen. That's pretty impressive. I mean, the algorithms that run that software in there that takes this digital information in, turns ones and zeros into an actual usable picture is, it's so, I tell my students a lot of times, I love living in a digital world because all the analog stuff we used to teach and all the alignments and stuff we had to do, work on X-ray film processors, dirty, messy, smelly, ugly job, the time commitment, unbelievable. And now we take an X-ray and within 10 or 12 seconds, you have the full image. There's so much depth to that image too. There's so much pixel value information on each pixel that, and we're talking about shades of gray. I'm going to show you a couple examples here, but there is so much information in there rather than, if you think about an X-ray film too, that was a moment in time. That's unchangeable. It's how you, it's like going out with your Nikon camera and taking a picture of the sunset. You know, it is what it is for that time, that millisecond that you took that shot. With analog, that's the way it is. With digital now, it's a moment in time, but now we can have so much data there, we can manipulate that data. We can pan, we can zoom, we can use calipers to measure stuff accurately. We can window and level. If we don't like the way the image looks, we can change the brightness and contrast. With film, that was a no-go. The X-ray techs would have to march the patient back in there. If there was some kind of artifact, say the film processor put a scratch right through the chest or something on an X-ray. That wasn't the patient's fault, it wasn't an X-ray, but we still have to do a repeat because the film was scratched by the processor. Now, with digital, there's so much more. I'm just so happy to live in a digital age. So how do we capture a digital image? So I'm just going to run through this pretty quick. There's different ways. There's photocoupling, there's diodes, there's photodiodes, CMOS imaging chips now, but just in general theory, this is the way, and you see our little Nomad device up there too. And this is what the type of image now that we get our digital image of our teeth. So the direction of the X-ray beam is from bottom to top. We have a protective housing, and then we have something called a scintillator screen, right? That just means that radiation hits it and it gives off light. That's all it means. So we're going to couple that using fiber optics to either an imaging chip or an array of photodiodes. This was earlier technology when we still used photo optics. Now we're using straight digital. You're still going to see some of these that still convert, that still have the scintillator layer that converts light into electronic data through the CMOS chips. And then you see the beginnings of a cable out here. So in a dental practice, this is just a typical USB cable that goes to a computer running some software that can manipulate the image. So that's basically, you know, we're taking radiation, changing it to light. Light is exciting the circuitry and storing ones and zeros for us. I could give a whole nother class just on digital, you know, acquiring an image and processing an image. They don't give me that kind of time, but that's okay. So basically, it's not magic. It's just electronics and coupling a fiber optic, changing radiation into light. So this is kind of what I was saying about X-rays, right? If you look at your hand X-ray, anywhere where X-rays were blocked shows up white. Anywhere X-rays pass through without too much difficulty is going to turn out dark. Then we have shades of gray, soft tissue, right? In between the fingers, you see that was raw radiation, so it's blacker than black. It's the blackest the image is going to receive. The hardest bone substance, the calcium in your bones, and the density of bones create that white, or it was X radiation was blocked. So here's another kind of the same thing, only we have things out in the industry, digital panels. Pass this around too. Right, so it's the same theory, only on a larger scale. you know, this time the X-rays are coming in from the top, signified by the squiggly lines there. We come into a substance that converts X-ray to light. That's first generation. Second generation doesn't use that. It just uses direct electronics that capture the image. We build a matrix of ones and zeros. We have a row and a column situation where we have maybe 1,000 pixels by 1,000 pixels, 2,000 by 2,000, whatever. We store those ones and zeros, and then we read them out. With a multiplexer that just takes channel after channel after channel after channel, sends it to the processing computer. Those are all ones and zeros. The algorithms in the software knows what to do with that. If you're running a hand X-ray versus a skull X-ray versus a chest, it knows what to do with that image to make it look like the hand, right? So it's kind of magic if you think of the software that has the algorithms that knows. And this is after thousands and thousands and thousands of hand X-rays. They kind of know what it should look like. So we can use the algorithm. It's real data, but it can enhance the bones and in between the phalanges, and you know, just the shades of gray and the depth of image running that algorithm in the computer, right? So one thing you noticed about the panel that's being passed around, there are no wires. So early digital panels had to be wired with power and data transmission. So we used, we had two different cables. It was a tethered situation where it was still a portable panel, but we would put it behind the patient, but we had this long tether line going back. Well, can you imagine in an ER having a cable across the floor, being stepped on, rolled on, stretchers, tangled, wrapped around IV poles, you name it, it happened. I remember when I was on call, being called in to replace the tether panel on a lot of portable X-ray machines, just because one little break in the wire, you're done. Now we have this panel that's being passed around. Again, I love living in the digital age. I love it. Now we have a wireless solution. And basically, I won't go into too much heavy detail, but basically, and you know, we're using radio frequencies just like wherever the hotspot is in this room. When you walk into Kroger and your cell phone hits the hotspot, so you've got Wi-Fi on your cell phone, either at 2.4 gig or 5 gig, it's the same technology that we're using here. That has a transmitter in the electronics of it that's being passed out to the access point that's normally located on top of a cabinet or a ceiling in an X-ray room. And then that has an Ethernet cable that goes back to the computer that's receiving the data. When we go in to install one of these, you need what I call just a sniffer that can, you got an app on your phone or your laptop that can monitor all the radio frequencies in the room, either at 2.4 or 5 gig. And what we normally do is carry this around the whole room, down the hallway, anywhere where this portable is going to be, and we look for the highest amount of signal with the less amount of crosstalk. If you have these high peaks and they're narrow, that is an ideal situation. If you have lower peaks that span across the other signals, that's crosstalk and that's interference. So that image is not going to come across as cleanly as we need it to. So we go to the computer when we're installing these digital panels, and we give it an SSID and a password, just like you would if you go into Walmart and you can't get on their Wi-Fi because they've got it locked down with a password. Same thing we do on these, and we call the panels. If you have 3 rad rooms all in a line, how do we keep that panel from sending an image to the other room, right? So it has a different SSID and password, and the frequencies and the channels are changed just to make sure that panel talks to that piece of equipment. No sending images across the hallway or whatever. But this is just an example out of one of the manufacturer's service manuals, and they kind of give us, the channel, The channels that they want us to use, again, we sniff out and we pick the best ones for our specific install. And then it gets into IP addresses and stuff. I don't have a lot of time to go into, but the manufacturer will tell you what IP address they want that panel to be to talk to the computer that's on the same subnet, right? All right, so moving on to, our function. Basically, these are the things we do when we come into our annual maintenance, or, we're just doing a check. Visual inspection, functional check, and power cord. Power cord, you're gonna think, oh, that's nothing, we do that all day. The power cord on a portable x-ray machine, I usually every 2 years I replace it whether it needs it or not. If you think it's on a coiled recoil spring, and that goes in and out time and time and time every day, right? They let it go from about 5 feet and it recoils, boom, hits it. The 3 prongs on your outlet or your plug, that hits the ground. Those bend, all kinds of problems. So something that's simple, okay, it's a basic power cord, but it's important to check it on routine maintenance for sure. So visual inspection, what do we do? How are we doing on time? Oh, we suck. Visual inspection, I'm checking labels, stickers, indicators. Collimator has a tape measure. Oh, looky there. Inspector Gadget or whatever his name is. A couple things on the collimator that I need to mention, you might see this in a little bit, is there are dials on the front of the collimator with numbers on them, but the numbers really don't mean anything to anybody except the physicist who's coming in to check it annually right behind me. And basically, it's going to tell you your source to image distance. Source is the x-ray tube, image is where the plate is. So there's a specific controlled distance there for the type of anatomy. The x-ray techs know it. The numbers on the dial here are set to a 40-inch source to image distance. If I do it at 35 inches and I try to measure the x-ray field that I just produced, and I have my collimator knobs at let's say 24 by 24, it's not going to be accurate at 30 centimeters because 30 inches, because those dials are set at a certain source to image distance, calibrated. If I choose 24 centimeters by 24 centimeters square and I take a tape measure and measure it, it only is because of it's a certain distance, because like I said, it diverges as it comes out of the x-ray tube. So it gets wider the farther you're away from it, right? So just a little something, I have been on several calls after a physicist comes in and checks the machine and say, your field is out of tolerance. It's because the stupid set screws on the knobs have come loose and they're not pointing at the right one. I put it at the right distance. I make my shot. I don't pay attention to where the knobs are, and it's accurate as heck. So all I got to do is loosen the set screws on the knobs, tweak them back to where it looks nice for the physicist to be in the right scale, right? Collimator light. We have what we have known as a field light. So the field light's very important because before I make the x-ray, I turn on the light and it's going to superimpose a light beam to where my x-ray is going to be. So you can imagine that has to be accurately symbolic of where the radiation is going to be. So that's another test that we do. Collimator. We do a collimator check, like I just said. We want to see that the light and the x-ray beam are superimposed on one another. There's a little hint here. There's a little red dot or like a little dimple on the outside x-ray tube casing. That's going to signify where the actual radiation begins. Remember that electrons hit the anode, bounce down? That's the point in real space inside the tube, and that's a critical measurement. Like I use the term source to image distance. If I want 40, it comes from that dot, not the bottom of the collimator. So that distance has to be made up for. You might see this question again. The tape measure, if you look at a tape measure of an X-ray system, it's not going to start at 0 and go through 1, whatever. It's going to start at 10 or 11. Why? Because we have to make up this distance between where the spot is and the bottom of the collimator. So the tape measure has to be cut off to take up for that. You might see that one again. Functional checks, you know, we're going to go through all the knobs. We're going to up and down KB. We're going to drive the system around the department. We're going to check the locks, make sure the tube goes up and down and spins around. We're going to make sure the collimator is turned on. There's usually a couple ways to turn on the collimator light, either at the collimator or on the base of the portable X-ray machine, because the tech would have to be out at the tube all the time if they just to turn on the light, so they have a secondary switch that's on the base of the portable X-ray machine. The bumper is pretty important. If you run into something, it won't allow you to drive any further forward, but it will allow you to drive backwards. I've replaced a few bumpers in my time. You can imagine that X-ray techs aren't exactly treating this stuff with kit gloves, right? And then hand switch is a really important thing. I usually change those out on a PM frequently, because my theory on troubleshooting and repair, what does the customer touch and manipulate every single day? And that's going to be the power cord and the hand switch. Any knobs, especially if they're push buttons. Do you think they just barely tap it? So those kinds of things I usually have in my gray stock or my trunk stock as extras, so I can be the hero and come in and save the day in 10 minutes versus having to order a part and come in the next day, right? So here's what I'm talking about, the cord reel, power cord. It's a retractable cord. Hundreds of times a day that's going in and out, in and out, in and out. And those are wires that are bending, right? Set up for failure. And then, you know, you're going to hear arguments on both sides. You'll see our hospital grade plug there with the green dot. Does a portable X-ray machine have to have a hospital plug on, hospital grade plug? It's not clinical equipment, and the only time it's plugged into the wall is when you're charging the batteries. You can't operate, most systems you can't operate with it plugged into the wall. So that's a big question that's come up in the past. I don't have a theory either way. I'm good either way. I don't think it has to be a green dot myself. That's just my personal opinion. Yeah, put one on there. It's not going to hurt, but I don't carry them. I don't carry green dotted plugs with me, so I have to go down to Biomed and borrow. We don't use that term, Courtney. So hand switch, very important component. Without a hand switch, you make no X-ray, period. This is what gets everything started. There's a couple positions and what they do. The typical hand switch is a 2-position hand switch. So in the first position, called prep, we're doing these things. We're heating up that filament, we're running current, we're boiling off electrons, and to dissipate heat, you can imagine those electrons hitting that anode at a high rate of speed builds up a lot of heat. So we try to dissipate that by spinning. Also, we're not wanting to pit the anode by hitting the same amount of energy time after time after time and time again. So that's, once the filament is heated and the rotor's up to speed, we get a ready signal back to say I'm ready to go to the second position of the hand switch. After that, let's just say the battery is good in the panel and it's ready to make an exposure. There'll be green lights on the panel. That information is fed back to the control, and if all the factors are met, we push down the second position, and that's when that high voltage is applied to both sides of the X-ray tube, and that's when we have our X-ray. Only while you're holding the switch. If I let go, it's done. It doesn't continue on after I let go of the hand switch. And on most systems, you might see this question again. There's usually a little side button on a lot of the hand switches, and that's another way remotely to turn on your collimator light, your localizing light that we talked about, right? You position the patient, you think you're at the right source to image distance, you do one last check before you hit the button. You hit the side button, turn on the light, you look at the light that's on the anatomy of the patient, you say, we're good to go. So you make the exposure. Yeah, you might see that again. Cable maintenance, another important thing. Um, High voltage is going through these bad boys several times a day. Um, so we want to pull these out of the x-ray tube and we want to inspect them for any burn marks, frayed cables, bad insulation or anything. And then we also have a silicone grease that we coat this, is known as a candlestick for obvious reasons. Oops. Obvious reasons, candlestick, you got 3 pins. So what I normally do is take my silicone grease, I wipe all the old grease off, usually isopropyl alcohol gets it nice and clean. I apply, everybody, if you talk to 15 different imaging engineers, they get 15 different ways to put grease on a candlestick. Yeah. But we all have our way, you know. I just put a big glob between all the pins. I take a popsicle stick and rub down the shaft of the high voltage cable. What we're trying to do there is push all the air out of the system so we have no arcs inside. So that silicone grease is an insulating grease, and it's also dispels air. And so that's part of the routine maintenance. I don't know, this is kind of awkward to pass around. You can come up and check it out later. The key thing on the high voltage cable is the alignment pin or the key, and you might see this in a little bit. This arrow is pointing to the little notch on the side. That means that this cable can only go into the well in one direction. None of the pins will be crossed. You won't have a bad situation on your hands. There's only one way it can go in the well. The well's designed with a slot that key fits into, and just for our troubleshooting purposes, the reason it's even up here is that designates where the common wire is. You might see that. You might see that again. The key is the common wire, and then we have our small and our large filament on our cathode side, and then on the anode side, what they do is short all the pins together so we have full power on the anode, but on the cathode side, you need to differentiate between small and large filaments, so we have the 3 distinct pins. The key is the common if you're ohming out the cable. All right. Need to wrap this up. So testing is another important aspect of what we do, right? So there's a few things that are very, very critical on our calibrations. You can imagine kilovoltage. We need to verify. If I'm shooting 100 kV, I want to make sure it's within 2 or 3% of 100 kV, depending on the manufacturer's specifications. I don't want it to be 110. I don't want it to be 70, because that anatomy and the program in the computer is set up for a certain kV and mass, and that's what we want. So we have to ensure as engineers, you know, that the accuracy of that. To do that, you know, we have these different manufacturers out there, but I happen to carry around a RaySafe X2, and plug and play, turn it on, put the probe in, take the shot. It's displayed. It even gives you the kV waveform on this particular device if you slide some screens. But anyway, what I'm going to do is I'm going to go in here and I'm going to set the generator at 75 kV at 10 mass. I'm going to take the shot. I'm going to look on my, I'm going to check my waveform for flatness, and I'm also going to check to make sure that's within about 2% plus or minus 1 kV, and go up through the scale, 60, 70, 80, all the way up to 120 kV, make those shots at different masses. And as you know, from troubleshooting in electronics, to accurately measure MA, I have to be in series with the wiring. So there's usually a circuit board somewhere in the generator with a jumper plug on there. You have to pull the jumper plug up. Another reason I carry the X2 around is with a special cable. I pull that jumper plug. I can actually measure MA. I don't need a separate meter. Different companies, when I was a vendor for company XYZ, they sent this little piece of equipment here, and that's, I'm being kind when I call it a piece of equipment because it was really crappy. it was just a cheap alternative to an MA meter. But anyway, those are the factors that we're checking. Again, we're going to check the coincidence of the X-ray field to light field, and that's what you see, the little copper phantom here with the rectangular square. I'm going to close my collimator blades using my localizer light, and I'm going to use the perpendicular cone there. That's a plexiglass tube with a BB at either end. If it's perfectly perpendicular, the BBs will rest on top of each other or very close. It's hard to see from this picture, but there are two BBs in the center of that bullseye, and it's within 1% tolerance. So when my X-ray tube is vertical and I close my collimator blades, I can do a couple different tests all in one X-ray shot, right? Okay, so this is kind of going over some information we've already been over. The only reason this is up there is because you see the little inspector gadget up there. If you've set up your home Wi-Fi, it's exactly the same. We got 2.4 gig and 5 gig, and the difference between those is 5 gig has more penetrating power. I'm sorry, is faster. 2.4 can go through solid objects, but it's not as fast, right? So low frequency, better penetration. Higher frequency, we can get some interference with some solid objects. So again, I take my Wi-Fi sniffer in the room. I find the channels that are the highest peaks without as much crosstalk, and those are the channels that I try to set my system up. Channels on the 2.4, channels on the 5, you can separate them, or you can use both. It really doesn't matter in a lot of manufacturers.